Okay. Okay. Good morning. My name is Okuyi Waduka. I am a final year student in the Department of Mechanical Engineering undergraduate studies. So I will be taking you on Continuum Mechanics tutorials today. I've been directed by Dr. Adeomi to, can I share my screen? Sorry. Let me try to do that. Okay, I think I can. Okay, sorry, can everybody see my screen? Let me just be sure. Any response? So if you can see my screen, please.
Yes, you can see your screen.
Okay, thank you. So yeah, so as directed by Dr. Adeomi, because I had solved some questions in the past that are in the tutorial videos, I'm just going to be taking some of them that I didn't cover, which run from questions 1.19 that I have here. This is in the chapter 1 book, by the way, the chapter 1 document, review of vectors. So I'll be running through questions from question 1.19 down to question 1.24. So 1.19, 1.24. So this will be the scope of our tutorial today, but then after this we'll have a coding session. So if you have any questions concerning the syntax of Mathematica or how to make things easier for yourself, let's say you're not the type who loves to code per se, how to make things easier for yourself and that sort of thing. So we'll handle stuff like that so that you'll be able to take your self-test and do well. So starting from question 1.19 or question 1.19 rather. Before we begin, I'd just like to, for the benefit of those who don't fully understand the concept of a dot product and a cross product so well, right? So when you're dealing with vectors, essentially you have 4 types of products. The first one is called vector scaling. So I'll just write scaling here, right? A vector scaling is just you have a vector, let's say a 2D vector like this, and then you multiply the vector by 4. So it just increases in size like that kind of thing. So that's scaling. So it's like you're multiplying a vector by, I want to use the word number, not scalar, because I'm still getting to that. You multiply the vector by a number, and the vector either grows or it becomes smaller. That's one. The second one is called a dot product. But don't let the name deceive you, right? A dot product is just called a dot product because instead of using multiplication sign, this time sign, you use a dot. That's the only difference, right? No, that's not the only difference, I apologize, but that's the reason why it's called a dot. But to make it easier for us to understand, for this class, we'll be calling it a scalar product. It's called a scalar product because when 2 vectors multiply themselves using a dot product, they, would I say, give birth to a scalar, right? So you multiply vector u by vector v, right, using a dot. You are going to get a scalar as your answer. That's why it's called a scalar product, because the result you get from that product is a scalar. The next one, which can be scary at times, is called the cross product. Again, it's only called a cross product because, it is a cross that is used to indicate the type of product it is. But its alias, or would I say nickname, is vector product. So it's a vector product. Just as I explained for the scalar product, it is only called a vector product because when 2 vectors undergo a cross product or a vector product, they tend to result into a vector. So 2 vectors, u and v, they undergo a cross product or a vector product together, or they are multiplied using a vector product. The answer you get is a vector. Last one is called a dyad, right? I'm sure this course might be the first time that most of us will be hearing that word dyad, right? This course is actually my first time hearing that word. So it's a circle and then an X inside. And don't let the word scare you. Again, it has a nickname. It's also called tensor product. All right. Even on Mathematica, when you want to carry out a dyad product, it's is called tensor. The command is tensor product. So it's called a tensor product. Why? Because when two vectors undergo multiplication using the dyad product or using the dyad, right, they birth a tensor. It's just as simple as that. So when you see dots, you're expecting your answer to be a scalar. When you see cross, you're expecting your answer to be a vector. When you see dyad, you're expecting your answer to be a tensor. I hope I didn't mix that up, but I mean, this is basically it. So that's that for now. Is there any question before I move on to question 1.19? I'll give like a minute for that. If there's no question, I'll just move on. Less than a minute, actually. All right, I believe there's no question. So let's move. Let me erase all these things I have here. So the call is being recorded. So in case you didn't take these notes down. So is there a question? Just for my no question. Okay, that's fine. That's fine. So yeah. So question 1.19 is saying that given three vectors, so we have three vectors, U, V, and W. If you read through this particular book or document, you will notice that scalars are represented by small letters, but they are not bold. They are not in bold. They're just regular small letters. But vectors are bold letters, right? But because we can't, I don't know how to replicate a bold letter using my writing, I'll just put an arrow at the top like that. So this is to show that this is a vector, that U is a vector. So we have three vectors. And sorry, for tensors, we use capital letter, bold capital letters. But I think in chapter 2, it'll be more clear. So we have three vectors, U, V here, and then W, right? And the book already says that using this result, so we have like something written down for us already that we should use as reference, right? So we're told that if a cross product takes place between two vectors like this, W and U, and then one of these vectors, which is W, does another cross product with V, right? And then a cross product is done between the results of both scenarios. What we would get is a dyad product of W with itself, or a tensor product rather, then multiplying a cross product between U and V. So just to check for, would I say dimensionality now? This is a vector, this is a vector. So it's possible for a vector and a vector to do cross product together. When they do cross product, we're expecting a vector. So if what we have on our left-hand side is going to result into a vector, we expect the one on our right-hand side to result into a vector. Now, we have a tensor here, W, dyad, W, that's a tensor. So when a tensor acts on a vector, what we get is a vector. So we're correct on that front. Anyway, I think chapter 2 might explain that relationship a bit more. But for this question, you don't really need that particular knowledge. So that being said, let's move on. It says that we should show that this relationship exists. Okay. First things first, there's a square bracket. We've not seen that before. There's a square bracket. Then we've seen a cross product between U and V. Then we have a comma. We have V cross W. Like that. Sorry, I apologize. And then we have W cross U. Now we are seeing on the right-hand side another square bracket like that. So the question is, what exactly does this square bracket mean? When I write three vectors side by side and I use the square bracket to house them, like what does that actually mean? Well, what a square bracket is a triple, would I say triple dot product? Yes, it's a triple dot product. So when you have a square bracket and you have three vectors inside, it's a triple dot product, right? Or a triple product, where this just translates to A dot B cross C. And we would see from questions in this particular document that this dot and cross are interchangeable. and the letters here are interchangeable as long as they follow the same order, ABC, BCA, or CAB, like that. You can always change the cross and the dots. So basically what this is telling us is, let me erase this. When we take the triple dot product of what's on the left-hand side, we're going to end up with the square of the triple dot product on the right-hand side. So let's go ahead and solve. We need to arrange this particular expression on the left-hand side in such a way that it aligns with the proof we were given in the question, which is W cross U cross W cross V equals W dia W U cross V. So this is what we're going to do. Triple dot product. I can write it like this: U cross V dot V cross W cross W cross U. Now, is this correct? Or is this in the right order that we need it to be? The answer is no. Why? Because here we have W cross U and we have W cross V. But here we have V cross W and then W cross U. At least for us to even interchange I'm going to highlight that in blue now. For us to be able to interchange what is inside this bracket here that I've underlined in blue, we should at least have W in front here and V here. How do we do that? When you have a cross product and you put a negative in front, what happens is that the two vectors that are undergoing that product will exchange. A cross product is not commutative. I think that's the word, because for a cross product, A cross B equals minus B cross A. Try to digest that for now. Probably when you watch the recording, you'd understand it a bit better, but that's just the relationship between two vectors that are going in cross product. So I want us to have this particular relationship. So what I'm going to do is I'm going to negate this whole thing and say minus U cross V. So that means this is equal to what I'm writing under is equal to minus U cross V dot. Then we have W cross V. I've done that switch that this minus accounts for, cross W cross U. Is there any question as to how I got to this point so that I can explain? Any question on the triple dot product? Any question on what's it called now? Triple dot product, on the commutative nature of, or the non-commutative nature of cross products? Any question on that before I move on? I'll give you a minute. Well, less than a minute actually. Okay, so nobody has unmuted themselves, so I'll continue. Sorry, permit me to open up Paint on my laptop so that I can use the right-hand side to solve as well. Paint. Okay. So I want to use that on this side. Sorry. Yeah. So this is where we are, and we need to continue. So we have this, and we can relate the two last terms in this expression, right, to the proof that we're given at the top. So I'm just going to draw a circle here. We can relate what is inside this circle to what is at the top.
Hello.
Yes, hello, I can hear you.
Yeah, please, admin, please do me a favor. People might still want to ask a question between the minutes you've given them. So please, you should decide after the minute has elapsed, then you should continue with the lecture, because some people might still be thinking within that minute. So don't allow anybody to just say, okay, there's no question. If that minute has elapsed, then you can now continue with the with the things you are solving on the screen. Thank you very much.
Okay, I'll do that. Okay, thank you very much. I'll do that. So I'll just set a timer for 1 minute so you can gather your thoughts and then continue. All right. So let's continue. So I have drawn an arrow this is what we want to relate to the proof we were given in the question. You didn't have to prove this yourself. It was given to you already, right? You're just supposed to apply it. So now we have minus U cross V dot, we're going to do this exchange now, dot W diad W. In this case now it will be V cross U. Are we together? Any question? Okay, I assume no question. So there's a method I have in mind. Let me just check what was done in the tutorial so that we're all together. And then I will, okay, it's the same method I have in mind. So let's continue. Now, this question is a, yes, please, I can't unmute. Okay, sorry, Mr. Ade, I think somebody said they can't unmute. I think they want to unmute themselves.
Please always raise your hand if you want to get on. If you want to unmute, raise your hand and I will mute you, please.
Yeah. Sorry, Mr. or Miss or Mrs. Mojirade. I don't know. You'd have to raise up your hand to ask the question.
Hello.
Okay,
I've
yes.
raised up my hand. Yeah, good morning.
Okay.
Please, can you go over the
Good morning, ma'am.
Yeah, the one you were explaining now, the three methods, the way you change the lettering to have a negative as a negative sign on it.
Okay,
Can
so
you go
that's
over it?
let me just confirm what you're
That's
asking,
from
like
that
how I
square,
got from here to here.
from the square. No, from the square. From the
Which that's in red.
UVW squared. No, in black.
UVW square. Okay.
The
How
square
I got
bracket.
from
Yes,
this.
exactly. Yes, from that
Okay.
downward. Thank you.
Okay. So actually so this is the question. Let me just circle it in blue. Again, thank God this is being recorded. This is in blue. This is actually the question. So I'm trying to work my way from the left-hand side to the right-hand side. I haven't gotten here yet. I haven't gotten to this point yet. So I'm trying to work my way from here to here. So this second line you're seeing that I just did a tick on now is the second step from the left-hand side here. This is left-hand side. How I got from this particular point was that I said that anytime you see a three vectors in a square bracket like this, let's say A, comma B, comma C, anytime you see them like this, it means that they are undergoing something called a triple product. I believe it's a triple product or a triple dot product. I'll just put dots in quotes. I think I'll have to do a simple Google search to confirm that. Either it's called triple product on its own or dots is there, because I know there's something called the triple cross product. So it's called the triple dot product, dot in quotes, right? And what that means is, which is what we have here, because this is synonymous to vector A, this is synonymous to vector B, this is synonymous to vector C. So it's basically like saying A cross B dot C. I also said that the dot and the cross are interchangeable. So A cross B dot C is the same thing as A dot B cross C. So this is what I use to get this. So if you look at it, this one I said is synonymous to A, U cross V. This is what I have as my A here. Dot B, V cross W, cross C, W cross U. Are we together, ma? Do you understand what I just said now? Before I now move from like this line, that's from this next line to, let me quickly check. Okay, yes, ma'am. All right, ma'am. So so that's how I got to this point where I did the tick. Now to get to the next point where I have this red circle, what I did was this. A cross product, as I mentioned before, is not commutative. So if you have two vectors doing cross products, like A cross B, you cannot say A cross B is the same thing as B cross A. They are not the same. However, A cross B is the same thing as minus B cross A. That means when we want to interchange it, because if you look at this, it has V cross W and then W cross U. We need something that has W in front for both of them. So W cross V, we need something like this, W cross V and then W cross U. For us to be able to do that change, to do that substitution, we need to negate that, we need to negate this expression. That's, we need to put a negative, just as I've done here for A cross B and B cross A. We need to put a negative sign. That is why I have a negative sign here. So putting this negative sign means that I'm able to say, instead of V cross W, I can then confidently say W cross V, because I have put that negative sign to account for this exchange that I have done. This exchange I have done, again, like I said, is just there because I want it to be in the same, you know, just like further math. If they tell you, or if they tell us, oh, let's say sine square theta plus cos square theta is equal to 1. Prove that so thing is equal to something, right? You're going to have to follow certain steps. You're going to have to know certain rules to get from point A, that's the left-hand side, to the right-hand side. So these are some of the rules. E.g., when you have a triple dot product, the dot and the cross are interchangeable. That's one rule. Another rule is a cross product is not commutative. You have to put a negative sign. That's another rule. So these are the rules that we're following. And another rule they've given us, I mean, the question is that W cross U cross W cross V is equal to the dot product of W with itself acting on U cross V. So we need to get our, I think somebody asked a question. Okay, nobody did. I think some people are in the waiting room or something. Okay, anyway. So we have W cross V cross W cross U. So now we can take it to what the question gave us to use. This particular proof that I have in red. So this is how we ended up on the right side of my page, where I have minus U cross V dot W brackets V cross U. Now, another rule we need to know from our dyad. One thing we know about the dyad is that when you have a dyad, dyad product, A dyad B, like this, and both of them are acting on a vector C, this is as good as saying A times B dot C, I believe. Right? So, since we know this, in this case, our A is going to be W, our B is going to be W, and our C is going to be V cross U, right? This is V cross U. So we can continue. Now, we're going to use that rule I just wrote down. So that's going to be minus U cross V dot, now A, which is W, bracket B dot C. So W dot V cross U. Right? Now, looking at this, we still have this negative sign here. We need to take it out. So, two things we can do. Either we change this U cross V to V cross U. Let me put that in blue ink. Either we change this to V cross U, or we change this one here to U cross V. Well, I normally like U before V, that kind of thing. So I'm going to change the one on the right-hand side. So what we're going to have is U cross V. The minus sign is gone now because I want to do another switch. Dot, this W can come out as a vector that's just acting on a scalar here. So this is W. So we can have this here. And then we have W dot U and V and U switch. U cross V. What does this look like? Sorry, before you ask, I'm coming. Let me just, sorry, I'm really sorry. Let me just finalize the question before you ask. I'm sorry, because just one line left. So this looks like a triple dot product. I apologize. A triple dot product, right? We have U, V, and W. So that means this is essentially U, comma V, comma W times W, comma, I don't know why my mouse is behaving like this, I'm sorry. W, comma U, comma V. Because U, V, W follow the same order, W, U, V, or V, W, U, they are essentially the same thing. So this is as good as saying UVW times UVW, which is the same thing as UVW square. So triple product of UV and W. That is how we go from the left-hand side to the right-hand side. So sorry, sir. Sorry for interrupting you. This was your question.
All right. Thank you so much. Please, I want to ask from this part where you have minus U cross V dot open brackets W cross V cross W cross U. That's this part where you said from the when we go back to went back to the
Yeah,
question.
that's the last line over here on the left-hand side.
Exactly.
Okay.
Yeah. Looking at going back to the question, what we have on the question is saying W cross U cross W cross V. But what we
Yes.
have here is W cross V cross W cross U.
Yes.
So are we not going to do just as you did the negative, as you said that is not cross product is not commutative. So are we not going to still need to change it back to now to negative again, since we are calling this back? I don't know if you understand what my
Yes,
question
I
is.
understand. I understand your question.
Exactly.
So because we have W cross V here and W cross
Yeah,
U,
exactly.
whereas it's supposed to be
Yeah,
W cross U cross W cross V. Yes, sir.
exactly.
Now, most of these rules are essentially just placeholders. All these letters are placeholders. So what this thing is literally telling us is W should come first in both of them. Then if we have U first and then V second, we will have U cross V. This can be W, let me use another marker, let's say green. This can be W cross A, right? Cross W cross B. Essentially, this would be W diag W A cross B. It's the same way it can be W cross V, and then they're just placeholders, they're just letters. So they're just there to show you that, oh, put U before V when you're doing this cross product. However, what you said, sir, is actually very valid. You can do a cross product between these two cross products, right, to change them. Now, if we do that, you'll be correct, but you actually just spend more time on the question, right? So like, it's just going to be more steps, right? You'd have to change it, and then after changing, you'd turn this to a plus again, then before you now start checking this rule and getting it. So it's like one extra step. So what I did was a bit shorter, but what you did is valid, and you'd arrive at the same answer. So, or what you're suggesting is valid, you arrive at the same answer. So it's just one extra step of step of calculation. So it's possible to do that, but the reason I went through this route is because V and U and V, they're just placeholders. It can be B, A, can be C, can be Z, X, can be anything, right? They're just there to show you that if U is in the first bracket and V is in the second bracket, it should be U cross V. If it's A that they put here instead of U and B instead of V, it will be A cross B, that sort of thing. So it's just a matter of checking the order of the vectors, checking which vector comes first and so on. So okay, thank you very much. So any question on this? I would based on the suggestion that was made earlier, set the timer for 1 minute. I'll tell you when that begins, so that if there's no question, we will then just move to question 20. So the timer starts now. So in 1 minute, if there's no question, we'll move on. Well, I think because of time, I mean, 30 seconds has already been elapsed. So if it's possible to type in the chat that you have a question, I will go back. But just because of time, we have, I think 5 more questions or so, 5 more questions to solve. So let's continue. Anyway, so we're done with this question. I'm going to clear my screen now. You can always get it from the recording that is going to be made available to the class. So I would close this. And now we have question 1.20. Similar question. Given 3 vectors UVW, show that this, right? We should show this Are we really meant to show it? Okay, we'll show it. I mean, because we're asked to. They didn't say we should use it to show something. Instead, we should show it and also show something else. We should show that for a unit vector E, a unit vector is just a vector with a magnitude of 1. So we should show this, right? And after showing it, we should say that this is equal to what they have here. So let's begin. I would start writing. So this is, again, U cross V cross W cross V, right? Let's look at it analytically or closely. I think that's the wrong word, but anyway. W cross U cross W cross V. There's a rule that we should all be familiar with, I believe, right? When you have A cross B cross C, essentially, it gives you B A dot C minus C A dot B, essentially. C A dot B. Let me just be sure. This is A, this is B, and this is C. Yeah. There are other variants to this, but they all like arrive at the same answer. So this is just one of them, and it's a correct one. So I remember this because it has the acronym, or you can use the acronym BAC cab to remember it. BAC cab. So when you have A cross B cross C, is BAC minus cab. So BAC cab. That's how I always remember it. So anyway, since we have that, we're going to use that same idea to solve this. What I have done is a cross product gives you a vector. So let's just take this particular cross product to be one vector A. So this will be our vector A. Then this will be vector B here. This W vector B. Then this V vector C. Now, without using what's it called now, indical notation, let's just go straight away. We have this to be A cross B cross C to be BAC cab, as I just said before. So basically we have A cross B cross C. So that would be B A dot C minus C A dot B. Now what is our B? Our B is W. So let's go. W. What is our A? W cross U. So that's W cross U dot V, because V is our C. We have that back. So this is B, A is W cross U, and C is V. Now moving on, what is C? C is V. What is A? A is W cross U. And then what is B? B is W. So we have W cross U dot W. I'm going to do something now. And that is to cancel this and see that all of these things we're written here on the second term is equal to 0. Why is it equal to 0, you might ask? The issue is that we have a certain thing there, which is W cross U dot W. Permit me to just divert a bit. Why did I say everything is equal to 0? That's what I'm trying to answer now. So essentially, what is a dot product? A dot product, when you find a dot product, it gets you the projection between two vectors. So how this is projected on this vector, or how this is projected on this vector, that sort of thing. Now, a cross product, however, what does that do? We were taught right-hand rule sometime in our lives, right? And that right-hand rule says when you have a field of current or something, and I think like this, and like that, basically. What a cross product does is that it takes two vectors. You do cross of two vectors, and it gives you a vector that is normal to their plane or perpendicular to their plane. I think a question just came in. Oh no, I think someone is in the waiting room. Okay, so it takes two vectors like X and Y. Let's say we have this vector Y and vector X in the Y and X directions, right? And when you take the cross product of these, it just gives you a vector that is perpendicular to both of them, something like Z, right? Not something like Z, in this case, to give you Z. Now, what is the issue and why did we turn it to 0? We know that when two perpendicular vectors do dot product with each other, they give you 0. Why? Because dot product is related to cosine. And cos 90, when they are perpendicular, cos 90 is equal to 0. So whatever vector was found by W cross U is going to be inherently perpendicular to W, because W was part of this cross product. If we wrote U here, it would be the same thing because it's perpendicular to U. So what we get from this whole thing is 0, strictly because we have W cross U dot W. This particular thing, I think, is explained in an earlier question between questions 1 to 10. One of those questions there in this particular document that we have. So if you need more insight on that, I think you can go and check that. But that being said, we have this right here. W brackets, then the triple product of W, U, and V. Essentially, this is a triple product. This means that the cross and the dots can interchange. We want to show that what we have here, W cross U cross W cross V, gives us that certain dyad. So to do that, we are going to interchange the cross and the dots. Like I said, it's possible to do that, and it's not wrong. So this is W dot U cross V, like that. What does this look like? This looks like A brackets B dot C. And if we're working backward, we know that this is A dyad B acting on C. Just take some time to digest that. First and foremost, I switched the signs, the cross and the dots. I switched them. That's why instead of W cross U dot V, is now W dot U cross V. I switched them because that's permissible, is allowed to do that. You're allowed to do that rather. Now, after doing that, I sort of made this a bit familiar. We know that A dyad B acting on C is same thing as A bracket B dot C. Now, if this W is our A, this other W is our B, and U cross V being a vector is our C, and it's possible to relate them with this expression. In that case, this would then give us W dyad W acting on U cross V. That is exactly how this was gotten in 1.20. At least for the first part of it, because the first part says we should show this expression, W cross U cross W cross V is equal to this. So we've shown that. Is there any question before we move on to the second part of the question, which talks about the unit vector E? Any question? I will give 30 seconds for that. So in the absence of questions, so the timer is going. In 30 seconds, if there's no question, then we would have to move on. But if there's any issue that isn't raised here, it's always possible to rewatch the recording and get it out. Okay, timer is up. Let's continue. So we have found this, that W cross U cross W cross V is equal to that. Now, let's see how the triple product of, all of this that we have here is equal to the triple product of E, U, and V. So let's work toward that. Okay. Let me just erase all these. I'm not going to erase the final thing. So we have triple products of E, E cross U, and E cross V. Easy as that. This is E dot E cross U cross E dot V. And like I said, when I was answering the question that came in about switching U and V, E is just W is just a placeholder in this particular expression. So in this case, instead of W, we are going to be working with E, right? So this is E. Now W cross U, in this case, is going to be E cross U cross E cross V. This is now going to be dot E dyad E and then U cross V. All we did was just to replace W in this expression with E. Now, we have a diode product here. Let's work on it. Again, I'm going to write A diode B acting on C is the same thing as A bracket B dot C. Simple as that. So let's work. That's E dot, I'll put a square bracket. In this case, this is A diode B, so E diode E, and then this is C. So A is going to be E, B is going to be E, and that's going to be dots U cross V. Now, this E that's here can come out because it's just multiplying a scalar at the end of the day. So this is going to be E dot E multiplying E dot U cross V. Now remember, E is a unit vector, magnitude of 1. So E dot E gives us 1 at the end of the day. It gives us 1. And we're left with this triple product, which can also be written as E, comma U, comma V, as we stated earlier. So any question? I have my timer set. Is there any question? So that we can unmute and ask. Okay. In the absence of questions, then we can simply move on. So we're done with question 20, just like that, and we'll move on to question 1.21. Okay. Now, question 1.21 says, given that U, V, and W are vectors, find the values of the scalars alpha and beta in this equation. So we have U, V, and W, and we're supposed to find. Yes.
So sorry. Sorry, my hand was raised the other time.
Sorry.
I was trying to stay away from a noisy place. So okay, thank you for undoing the. So
Yes.
I was going to ask about this ABC. Understand?
Yes.
So suppose we use where we have E.
Yes.
E dot I've forgotten that symbol.
Diode
E, and we represented AB on it.
Yes.
So suppose we use that E diode E as A alone, and then U and V as B and C.
B and C.
Would it still give us the same?
Very good question. It won't. Earlier on in the class, I mentioned that a diode product, right? A diode product, E diode E. We've been getting away with, let's say, calling U cross V a single vector, like let's say A. You've been getting away with it. Why? Because a cross product gives you a vector at the end of the day. So that A you are calling is still going to be a vector. However, E diode E doesn't give you a vector. So you cannot just assign a vector to it like A, like that, right? So it gives you a tensor. It gives you a tensor. It's also called the tensor product. I mentioned that at the beginning of the class. So we can't essentially do that because E diode E is not a vector, it's a tensor. So this A here is a vector. In this particular formula that we have here, that A, let me use another marker, that A diode B times acting on C is A bracket B dot C. The people who came up with this, or the mathematics behind it, is implying that A is a vector, B is a vector, C is a vector. If we put a vector where a tensor is supposed to be, we will not be able to get the right answer. We'll not be able to get the right answer at all. So that's why I didn't do that. Rather, I took A, and because E itself is a vector. E is a vector, not E diode E. E is a vector. This other E is a vector as well. So I said, okay, let A be E or E be A, and then E be B, that sort of thing. Then C, U cross V, because U cross V is a vector. I don't know if you understand. So it's a matter of dimensionality, if I may say, because the vector and the tensor are not the same. Okay, thank you very much. So I believe we can continue. Let me get my eraser, or not, clear all drawings. So moving on to question 1.21. We can see that indical notation was used to solve this question. The other questions we've been solving are straight. Now, for indical notation, I'll just write two things, which I believe would have been given in the tutorials before, or the recorded tutorials that you'd have been asked to watch. We know that when a dot product, I'm just saying this in case we encounter this, when a dot product is given for a vector A and a vector B, I apologize for not using arrows for the other vectors I've been writing since. This is essentially a dot product between AI, EI, this is in the component form, dot BJ, EJ. So essentially what we have is AI and BJ, they are scalars. So they can come out and multiply each other. So that is AI, BJ. Then the people who have, or the components or the items that have dots between them are actually the vectors, which are EI and EJ. So that's EI dot EJ. At the end of the day, we'll have something called the chronicle delta. I'm not going to get into what that is. So it will be AI, BJ, chronicle delta, IJ. And that's essentially AI, BI, or AJ, BJ, like that, AJ, BJ. That's for dot products. For cross products, however, this is AI, EI, cross BJ, EJ. AI and BJ, they are scalars, so they can come out. So this is AI, BJ, then a cross between EI and EJ. Are we together? So basically, when you cross EI and EJ, you get introduced to something called a Levi-Civita symbol. I think we would have heard about that before. So AI, BJ, EIJK, EK, like that. This EK here is a vector. So that is what we have. Now, I have said this, I apologize. I just wanted to rewrite the arrow. I have said this because we need this cross products indical notation form to solve that question 1.21, or to understand how it was solved. So that's why I wrote it down. And then I wrote down the one for dot product, just in case it comes up at any point. So let's solve. I'm going to clear my screen. So clear my screen. I have that. We're supposed to show that, or we're supposed to get the scalars that multiply U and V when we do a triple cross product between U, V, and W. So U cross V cross W. Good. Now, we'll take it step by step. It's going to be difficult to do a cross between these three all at once. So we'll do a cross between U and V first, before we now do a cross with W. So crossing U and V, from what I wrote before, U cross V, using that same format. With practice, you'll be able to write it fast like this too. UI, VJ, EIJK, EIJK, EK, like that. Simple and fast. Same thing I wrote down there, but instead of U and V, I just used A and B. Moving on, we want to cross this particular one with W. So we would have a cross product between UI, VJ, EIJK, EK, cross. Now for W, I have to find another letter. Let's say WL, EL. All the scalars can come out. So UI, VJ, WL, EIJK have come out. And what we have is EK cross EL. Now this is UI, using that same logic that I taught before I wiped the board. This would be UI, VJ, EIJK, would I now say KL and then introduce a new one, MEM? This is correct. However, it is not the best form. We have to do something
Hello, sir.
called, yes, ma'am.
Hello, sir. Please,
Yes.
how did you get WLEI?
No, WLEL. Basically,
LEL.
yes. So basically, we can use any letter we want. So I used the L and L instead of I or J because we already have I for you. We have you as I. Normally, it's not.
What I'm trying to say is that, sorry.
Yes.
And the first question, the first one we expanded was U and V.
U and V, yes.
U and V.
Yes.
Then the next one we now have to combine it with W. So is that W the WLEL?
Yes, that's this W from here.
Okay.
The W from the question,
Thank
yes. Yes, ma'am.
Thank
Thank
you.
you, ma'am. Yes, ma'am. So, okay, all the scalars have come out, and now we have this. There's a certain name this is called. I am very sorry that I cannot remember. But when you have two Levi-Civita symbols and they share at least one letter, you have to do some subtraction. Is somewhere in this chapter. I've forgotten the exact name, the name it is called, what that process is called. But we're going to do that now. I mean, it's in the chapter, so with practice, you'll be able to do that. But for this question, I won't run through how to. I'll just show you the application of doing that. First things first, we have IJK, we have KLM. K is common in both of them. But we need this K to be in such a way that it is in the same position. So if K is the first letter here, K must be the first letter here. Or if K is the third letter here, K should be the third letter here. Anyone you feel like doing. So what I'm going to do is I'm going to make K the first letter in the one on the left. You can do it that one. Either you change the position of K here or you change the position of K here. So change the position of K in the first one or in the second one. I want to change in the first one because I want K to be at the front. Okay. So we're essentially going to have UI, VJ, WL, EKIJ, EKLM, EM. Great. K and K are in the same place. When we have two Levi-Civita symbols, we're going to do, I'm sorry, I think I might need Dr. Adilmi at some point to just clear this out because I've forgotten the name that is called. It's a substitution. But we're going to do that now. So this gives us essentially UI, VJ, same things that we had in the previous one. Now, when it comes to the Levi-Civita symbols, there's a bit of EM, let me write that. There's a small problem. That's substitution. How do we do it? We take the first, so K is common, so we're not going to even look at K side at all again. K is dead to us. So we'll take the first letter that is not K and the first letter that is not K on both sides. So we say Chronica Delta IL. Then again, Chronica Delta JM minus Chronica Delta IM, Chronica Delta JL, right? So, I mean, we treat this like normal multiplication. We'll treat this like normal multiplication, and we know that the Chronica Delta symbol is used for substitution. So that's what we're going to do. I'm going to just go through it step by step, as simple as I can, right? If there's any question, please don't hesitate to ask. So I have Paint. I have Paint opened up rather, and we're going to move. So this is equal to UI VJ WL EM Chronica Delta IL Chronica Delta JM minus UI VJ WL EM Chronica Delta IM and Chronica Delta JL. This is a minus sign, so it's the one at the top minus the one at the bottom. All I did was to expand what's in the brackets. That's all. Okay, I just saw a chat coming. Oh, you say Mr. Bolaji's hand is raised. Okay, would it be possible to ask the question now?
Thank you. Please, when you change the position of K,
Yes.
from the third place still to the first place in order to make it rhyme with the other one,
Yes.
doesn't it have any effect on the sign of the vector itself? Like it's happened the other time, changing like that. That is one. And two, how did you come about the subtraction, the next line?
Okay.
Where you
So
have the conical I L, then conical J M minus
yes.
conical I M, conical J L.
Yeah.
Thank you.
So essentially, for the first one, we have I coming before J and coming before K. So I, J, and then K like that. So it forms like a cycle where I comes before J and J comes before K. So we must keep this cycle going. If we want K to be the first one, wait, sorry, please give me a minute. I need to be excused for a short minute, please, like 1 minute or 2 minutes. I apologize. I need to get something done because of the semi-storm that's happening outside. Sorry, I apologize. I apologize. Sorry, the storm outside is very bad. I had to take some things out. So now you have to just keep this order going. IJK or KIJ or JKI. The problem now comes when you reverse this, like IKJ or would I say JIK, that sort of thing. So it must be in such a way that it keeps with that order. So do you understand that? So what I did was that it is I, J, and K. I kept to that cycle. So that's how it ended up being K, I, and then J. That sort of thing. So that's the first thing. The second thing is, how did I come up with this chronicle delta subtraction here? Well, I will just point the class to it. It is, it was given in page, let me just get the page and then I'll come back. It was given in page, that's the page that talked about Levi-Civita symbol. That should be down. Let me just point the class to that so that we can continue. Okay, it was given in, yes, products of alternating tensors. This is page 27. This is page 27. So you can see here, I don't know how I'm going to, okay, let me clear my screen first. Let me clear my screen first before I continue. You can see here what was done on page 28 this time. RSK, IJK. They took the first letters, they took the second letters, and they took the first and the second, then the second and the first, like that. RISJ, RGSI, like that. So that's how that was gotten. So I hope that answers your question. So moving on, just so that we can solve this question and be done with it. Let me get my eraser to erase this. We know that the chronicle delta is a substitution symbol. So we need to substitute any I we see with L or any L we see with I. And then also any J we see with M or any M we see with J. So that's U I want to change any L I see with I. So that's UI, VJ, WI, and then EJ, like that. Minus, same thing occurs for the second term. That will be UI, VJ, WJ, EI. So I've done the substitutions. And what this gives us is UI, WI, VJ, EJ, minus VJ, WJ, UI, EI. UI, WI, as I showed before, is just a dot product of U and W multiplied by V, because VJ, EJ is V vector, minus VJ, WJ, which is V dot W, multiplied by vector U, like that. So, any question? Is there any question? Any question before we move on? Okay, I believe no question. But if there is any question, anywhere I am, you can always just stop me and then we can go back to this if there's need to. So this is what we have. And from the question, at least, we can then confirm that the scalar that is in front of you or that is multiplying you is, sorry, I think there's one in the waiting room. The scalar that is multiplying you is V dot W that we have here. And the scalar that is multiplying V is the U dot W that we have here. So that is what we have. Let me move back to the chapter 1 document. We're on question 1.21. So actually 1 hour has elapsed since we started this class. And I just wanted to know whether we're still interested in the coding session. Because Dr. Adeomi instructed that I probably spend an hour on the tutorial questions and probably 45 minutes on coding question. So is there any, do we move ahead? Does anybody have any question regarding coding in Mathematica? Probably any question regarding, oh, if you're not proficient in coding, how to still use it, and so on and so forth. Sorry, someone raised their hand, I believe. Hello?
Yeah.
Okay, I
Sorry
can hear
for
you.
stopping again.
No, it's not
Yes.
a problem. No, it's not a problem.
For the coding, the last video she sent to me, I was unable to do it because the font was too tiny for me. So I could not understand or go along with whatever you were explaining. So I don't know how you can help with Mathematica. For me,
yes. Okay, the font. Okay, but is there any specific question that maybe you encountered and you probably wanted to use Mathematica to solve, so that we'll use Mathematica to solve that question now?
well, the video was all about Mathematica, me trying to get used to Mathematica. But since I could not see what we are trying to explain, I could not practice.
Oh, I understand. I think I would have to speak with Dr. Adeomi about that.
Okay.
To probably reach a result, yes. Because I don't think I specifically prepared anything to teach in Mathematica. I just prepared to answer questions regarding like.
Or if you have any question we
and
can use now for Mathematica, which can also help. Any question available now to use on Mathematica?
Okay. Let me see. Let me clear all drawings. Let me look through the questions in the tutorial. Let me see if there's anyone that involves with numbers or something that we can work with. Okay. So I found one. This question 1.34. This is, we've moved from solving tutorials now to
Are we done with tutorial?
No, we're not done.
Jumping.
No, we're not done. I'm just saying, like, if anybody has any mathematical questions that they should ask, we will still go back if there's no further question. Yes, this just has to do with syntax of. You said? Oh, sorry, I didn't get that. But I think we would solve this question with Mathematica, and then if there's no other question, then we'll just go back to the solving the questions. In this case 22, 23, 24. So understanding mathematical syntax. First thing we need to know about Mathematica is that all commands begin with capital letters. Every single command you want to add plus. Well, that's a hectic way of adding, because you can just say 2 + 2 your normal way, right? And it will work. But every command you want to do, dot products, like cross products, dot products, tensor product, all of them will start with capital letter, like capital letter D, capital letter T, capital letter C, like that. Every single command in Mathematica starts with a capital letter. Now, we know that. Another thing we need to know is, if all of us have our Mathematica loaded, right? Let's try to run some simple codes. First thing is 2 + 2. You have 2 + 2. How do you run it? If you press enter, it's not going to run. So how do you now run it? The trick to it is that to run code in Mathematica, you hold shift and enter. Shift and enter. You hold shift, you hold enter, like that. Shift and enter, shift plus enter. So I don't know. Let me just even ask, does everybody have their laptops with them for us to practice Mathematica together? Or do I just do this and then when the recording is being played, we learn from that? I guess someone raise their hand.
Thank you. The issue I also encountered while trying to follow you while we were doing the tutorial in the one sent. So I couldn't use the brace brackets. I couldn't see how I could get the brackets, the call bracket and the brace bracket to use. Okay. I don't know whether it's part of the coding.
Yes, that is still part of it. So I don't know, depending on your keyboard layout. First thing I would advise, I'm seeing 2 charts here. Okay, you have your Mathematica, and then Mr. Godwin has his Mathematica. Okay, that's fine. The first thing I would advise is, my keyboard layout is English India. I think that's the layout that agrees with what we are being sold here in Nigeria. You know what was sold in Nigeria? On top of your letter 2, you have @ symbol and so on. But some people, if you press shift 2, it will give you another thing. So I think that's probably the issue. So first of all, get your keyboard layout to be in English India. You can always probably find this English symbol here and then click on more keyboard settings to get the layout you want. So here you have United States, United Kingdom. You can add the language. I would advise you add India. That's the one that works for me. So if you have that layout, your square bracket and your curly brace are on top of each other on your keyboard. On top of each other, meaning that for a key, these are 2 keys that I have on my keyboard like this. One is square bracket like this and curly brace like that. Then the next one is square bracket like that and curly brace like this. So when you press on this key without pressing shift, what you are going to get is this square bracket. But when you press shift, you press shift and you press this key, you are going to get your curly brace. You're going to get your curly brace like that. Are we together? I hope I'm able to answer your question. So first things first, change your layout to Indian English or English in India, right? And then after that, you locate your these keys the key that has the square bracket and curly brace on the left-hand side and the right-hand side. So anyone you want, if you want a right-facing square bracket, you just click on the key without shift and all of that sort of thing. I think that one is basic, but I think the major takeout or takeaway rather is the layout. Change your layout to English India. But if it's United States, I think it might be a different thing, that sort of thing. So that's to answer that question. So is there any other question before I continue with solving this question 1.34 using Mathematica? Any question? Okay, in the absence of question, I'm going to go ahead with that. So clear all drawings, and now I just showed you how to run your code using shift and enter. Okay, the next way to run your code, if you have 2+2, for those of us that have wider keyboards, you know, some people, their keyboards stop at the backspace, delete, row, or column. For those of us that have that extra keypad, it is only normal brackets, you call parentheses. Yes, oh, sorry. Okay, so it's only parentheses that's on your keyboard. I don't know. I think, anyway, I really don't know how we can solve this particular question, because I really don't know. Probably if you contact Dr. Adeomi, she'll be able to reach me for us to probably see, for us to resolve this probably within a short time or something. But I think this is something that can be resolved using layout or something. This to Mr. Abolaji. Okay, so the first way I showed us how to run our command is using shift enter. The second way to run your command, for those of us that have that extra keypad on the right, is to just press enter there. You don't need to press shift for this enter. The enter that is vertical. You know, we have 2 enter keys. The first one is horizontal. That's the one that you press shift enter. The second one that is vertical on your right, once you press it, it gives you your answer 4. I usually prefer this to shift enter, or I use them interchangeably. But those are the 2 ways you can run your code on Mathematica. Now, to solve this particular problem, we need to understand, first of all, that commands, every single command in Mathematica begins with a capital letter. We already know that since I mentioned that. And I said before that a dyad in Mathematica is called tensor product. Tensor products. Now, how do I know this? It's from experience and from using, I mean, if you're coding, you cannot know everything in the software. You can't know everything in Mathematica. You have to Google some things, right? So me telling you this now, you should know that when you use the command tensor product, in fact, let's type it out. Tensor product. As you type out the tensor product, look out for the suggestions. We have tensor product, tensor symmetry. We're interested in this. Once we click on this, I'll click on this downward arrow. You can decide not to, but I usually prefer to do that because it sort of gives me a template for what to write after it. So let's do that again. We have tensor product, T-E-N-S-O-R. I've seen it. I'll click on it, and I'll click on this downward arrow here. It gives me a template to use. So I can click on that, on this template. And then I want to find the trace between 2 vectors. We've not defined those vectors. Let's do that before anything. So let's clear that. I mean, I'll just show you how to find tensor product and how to use functions. But now, we want to find the tensor product between A and B. We need to first of all tell Mathematica that this is what A is. A is 3E1 plus E2 minus 2E3. And B is equal to all of that. We need to tell Mathematica that. How do we do that? Simple. Tell Mathematica A is equal to define a vector, use curly brace. So curly brace 3E1, 1E2, minus 2E3. This is how you represent a vector. I want to represent B now. So I put a semicolon. Anytime you put a semicolon, it will not print that particular line for you. It's not print the output of that line. So B is equal to 1, minus 3, plus 4, like that. Another semicolon. I have told Mathematica what A is and what B is. Now I want to find the tensor products between them, the dyad between them. So we just say tensor product right? Sorry, tensor product, the way I taught you how to do it, tensor product, click on it, downward arrow, sorry, T, tensor product, down, why is it not agreeing? Tensor product, downward arrow, then click on the templates, like that. I want to find the tensor product between A, where you have tensor 1, I want to put A there, and where you have tensor 2, I'll put B there. And I'll run it pressing this vertical enter. This is what we have. So 3 minus 9, 12, 1 minus 3, 4, minus 2, 6, minus 8. See it here. This is the answer that we have. To show it in a pretty format, you can use / matrix form. And it will give you in a matrix form. That is what you are looking for. That is how to find the dyad between two vectors. So you do that, right? Are we together? Is there any question? I'll give like a 30-second window before I move on. Okay. In the absence of any question, we've been able to find our tensor product. Okay, I see a chat. You are too fast. Oh, I'm sorry. Let me go back. I apologize. Okay, let me start again. I'll delete this whole row. To delete this particular input and output, I'll just click on this line here and I press delete on my keyboard. So let's start afresh. I want to define, or I want to get a tensor product between A and B. Remember, dyad is tensor product. I want to get tensor product between A and B on Mathematica. Before you can tell a computer, find me X plus Y or X times Y, you need to tell it what X is and what Y is. So let's tell Mathematica what A is. From the question, A is 3E1. A is equal to 3E1 plus E2 minus 2E3. To represent this in Mathematica, we say A is equal to, we're not going to write the E1, E2, or E3. We are going to use something called a curly brace because it's curled, it's shaped like this, curly brace, right? We're going to use that, and we're only going to use the coefficient of each of these unit vectors, E1, E2, and E3. So the coefficient of the first one is 3, comma. The coefficient of the second one is 1, comma. Coefficient of the third one is minus 2. Close curly brace. 3E1, this is exactly what we've written. A is equal to 3E1 plus 1E2 minus 2E3. That is it. Simple as that. Are we together? We have just defined A. To define B, we use the same method. We look for the coefficients of the unit vectors and we put them inside curly braces to be able to define them as vectors to Mathematica. So we are going to say semicolon. I'm putting the semicolon here. Why? Because if I do not put it, Mathematica is still going to print this vector A for me. I'm not looking for vector. In the same fashion is equal to curly brace, right? What is B? B is, let me just write it out before I type it. B is E1, so basically 1E1 minus 3E2 plus 4E3, right? Now, B is 1E1, so we'll write 1 there, comma, minus 3E2 minus 3, comma, plus 4E3, so we'll write 4 there. Close the curly brace. Are we together? We close the curly brace. So now, After closing the curly brace, we put a semicolon because I don't want mathematical to print B for me. I'm not looking for B, like I said. I'm looking for the tensor products between A and B. Now, to find that tensor product, I would use the command tensor product. I said it before. Every command in Mathematica starts with a capital letter. So to find the tensor product, I will use that command, tensor product, which is capital letter T. Then I will type out tensor. I'm waiting for it to suggest tensor product to me. I'll click on it. I would, or instead of clicking, I can press enter and press my downward arrow. It gives me a template. This way, if I don't know the arguments that go into this function, I am able to see that, okay, for me to use this function now in Mathematica, I need a tensor 1, I need a tensor 2, and it keeps going into tensor I, or to whatever tensor you're looking for, right? So I will click on this format because this is what I need, or this template. The tensor 1 in this case now, we're finding tensor product between A and B. The tensor 1 in this case is A. The tensor 2 in this case is B. And there's no other one, so we'll just leave it at that and we'll run it. I'm running it with the vertical enter, like that. I have run that. So this is what we have. This is actually a 3x3 matrix, but it looks somehow. I mean, if you gave somebody this kind of output, they'll be confused. Sorry, before I continue, notice I did not put a semicolon after my tensor product because that's the actual output I am looking for. That's what I am looking for. This is what I need. So I'm not putting a semicolon. I left it like that because this is the output. Now, going back to the answer that I got, this answer looks very ugly. Permit me to say, it doesn't look like the matrix I was looking for or the tensor I was looking for. To turn it to that form that we need, to turn it to that matrix that we need, I use // and I say matrix form. That is Mathematica, give me this thing in matrix form, and I press enter. Voila, it has given us in the matrix form. It is now more understandable for somebody to see. I hope we are together. Is there any question as to how I got from my inputs A and B to my output, which is the tensor product of A and B? Is there any question before I continue? Right, the class has to end maximum of 18 minutes time, so 17 minutes now. Okay, thank you. Okay, no problem. So no qualms. So we're going to continue and find the trace, because the part B says find the trace. Please, if we remember from our textbook, we know that the trace is actually just the sum of the diagonal elements in a tensor or in a matrix. We're expecting the answer to be 3 minus 3 minus 8, which should give us minus 8. Now, we know how to do this by hand. Now, how do we use Mathematica to solve this kind of thing? This is how we use Mathematica. The command for trace, in fact, let me teach this class like, people who haven't seen Mathematica before. When you don't know how to find trace or how to do any particular command, or like how to get a particular command you're looking for in Mathematica, you go to the help section and you go to documentation. In the documentation, let me wipe my board, sorry. So remember, you go to the help section. Let me close this. Let's say you want to find the trace. You don't know how to find trace. You don't know the command that is used to find trace. You go to help, you go to Wolfram documentation, and you just type here, trace. Well, no, not that trace. You're searching for trace. So it should give you a bunch of things to look at. Okay. This trace here generates a list of all the expressions used in the evaluation of an expression. That's not what we're looking for. We move on and we move on till we find what we're looking for. Good. We see here that TR finds the trace of the matrix. This is exactly what we're looking for. TR. The command is TR. It finds the trace of the matrix. You can click on that if we need more insight. So looking at this, when we find the trace of a particular matrix, it gives us that trace. In this case, the trace here is 15. So Using this information, we can close this and go back and say, yes, the command I am looking for to find the trace of the matrix before me is TR. I will press enter and press my downward arrow. TR is looking for a matrix that it calls list here. It's looking for a matrix. What's the matrix that we can give this TR for us to find the trace that was asked of us in our question? Well, we are looking for the trace of the tensor product of A and B. So we have the trace of the, we now put in tensor products between A and B. Let's look at it together. Inside this bracket, we have tensor product of A and B to give us this matrix. And then we have TR to find us the trace afterwards, right? I believe this is self-explanatory. Once we run this code, it's going to give us the -8 that we predicted is going to give us. So it literally just took the sum of the diagonal elements in this particular matrix, and it gave us that sum, which is our trace. Give us that sum. So any question, any contribution, any suggestion, anything that needs to be cleared before we move back to the tutorial questions that we were doing before the mathematical break, would I say, or the mathematical diversion? Okay, so somebody raise up their hand. I think the admin should have given you, I think you should be able to speak now. Yes.
Trace, I got lost the way you eventually got that trace after you got TR. Then when you click on TR, it brought out a certain other item, transpose and the rest. But say you say we are looking for TR of the tensor product.
Yes.
So the tensor product, did you write it or you got it as a command as well?
That's that tensor product. Yes. Oh, that I said that I know that from experience. I mean, I've been using Mathematica since Dr. Adeomi started teaching me continuum mechanics, which was in 2019. So I've been using Mathematica since then. So I'm familiar with a lot of the commands. So tensor product, I said it because I know that that's what we use for dyad. But I wanted to show you, in a case where you don't know what to do or you don't know what command to use, I wanted to show you that the documentation, the help tab is very helpful. It can help you to get any command you're looking for. Just type in the keyword, like we're looking for trace. Type in trace and just sort of read the short descriptions for each command that is there. It will give you the stuff, it will give you the, or it will give you a range of commands. So you just pick the one that you need, that sort of thing. So that's how we're able to get here. But for tensor product, that function, tensor product, I just from experience, because I know that's what we're looking for, I just said it. Oh, it's tensor product right, we're using. I hope that clears your question, sir. I hope that answers your question, sir.
But eventually, how did you get the answer from? Because I was trying to follow you, I'm using using the Mathematica. So I typed I got the command only TR. Yes. I couldn't get the trace itself. So that's my issue.
You typed only TR like this. Wait.
Yes.
Just TR like this.
Yes, TR like that. Yes.
Without anything.
And I have that transpose, triangle, and all that. That's what I got. So.
We transpose where? Oh, you typed TR
no, when
like
you type
this.
TR, see here, you have all these transpose, know those things, true,
yes.
triangle, and but I couldn't get it.
So you're asking how I got the template.
Yes. How did you go forward from here?
Okay. So what I did was I pressed enter, because when you see this stuff, you can just use your arrows to navigate. You can see how I'm navigating.
Yes.
So I'll navigate to the one I want, which is TR. I press enter and I press my downward arrow. Remember, I said that we actually need to see the templates, because this TR now, look at it. Yes. There's a situation where you will use TR and all you need to provide is a matrix, like this first one that says TR, then puts in a list. Sorry, let me just get back to that. I had to remove something from my screen. So there's a situation where you need that. There's another situation where you need to use a matrix and then comma a function f, I think, a function f or something like that. Then another one where you have to provide a matrix f and n. So we need to know which template suits us, and the first template actually suits us, because if you read the description, it says it finds the trace of the matrix or tensor. That's all we are looking for. We don't need any other thing. So we click on that and it gives us our templates. This thing here, this list is just a placeholder. It's asking you to put in something, put in a matrix. And the matrix that we want to put in, the matrix that we want to find the trace of, is actually the tensor product between A and B. Tensor product between A and B. So I'll just write this manually, A comma B, because of time. So -8. So I don't know if you get that, sir. Sir, was that clear? Hello, sir.
Yes,
I don't know
thank
if
you.
okay,
Thank
all right.
you.
Yes, sir. Thank you, sir. All right. So is there any other question regarding mathematical? Probably you opened it for the first time, it was a bit scary. You couldn't navigate, find a certain thing, so that I can just put us through all of that. Mind you, just a side note, personally, on a personal note, I prefer mathematical to MATLAB because it's more user-friendly, it's more beginner-friendly. If you don't code, if you don't know how to code, all this code we are doing today, it's just that nobody has asked any question regarding that. So I haven't answered. If you don't code, you don't like to code, but you know mathematics, you can still use mathematical without coding. It sounds funny, but it's true. Like, you don't have to type in any line of code. You can write things out as you do in your normal mathematics, and it will solve them for you like that. Since nobody has asked that question, we might have to postpone that hack, would I say, for another day. So I prefer mathematical. So I believe some of us might share that sentiment. So if there's any question regarding mathematical, probably you try to run a code and it's just giving errors, you don't know where the error is coming from, I think you should ask. Probably I'll just take questions now before we end the class, because we have 8 minutes left. So I don't think we'll be able to solve any question in 8 minutes. Is there any question? Okay, I think I'll just give like a minute. If there's no question, I think we can end the tutorial, because we might not be able to solve any full-blown question like question 22 in 8 minutes. That's the problem. So no question. Okay, then I think we can end the class. But if there's, I mean, when you watch the recording, if there's anything, you can always reach out to Dr. Adeomi. She'll reach out to me so that I can always help out with any problems that you might be facing concerning the use of mathematical, or even, I mean, use of mathematical mainly, because she's there for continuum mechanics. So I don't know. In the absence of questions, I think I can stop sharing my screen. And I don't know where we go from here. I think we can end the class, I believe. Sir, Mr.
I can go ahead and end the class.
Yes, since there's no question and the time has already gone. It's already time for me. Yes, sir. Thank you very much, everybody.
Thank you.